So now I would like to look at this from a different perspective. In the past 100 years, I would say the Martin Cooper observed something very interesting. So he concluded that indeed the number of simultaneous voice data connections doubles almost every 2.5 years. So indeed the cumulative development has been over a trillion times in the past 90 years, or in the past 45 years. There's a 1 million times more capacity increase. I would say this is globally. And if we dig into the details, you will see that indeed out of this 1 million times increase, there's a 25 times more because of the more spectrum available. And another 25 times is because we are using better modulation coding technologies. But for all the other 1,600, it's all due to frequency reuse, the increase of frequency reuse. So the frequency reuse basically is allowing different transmitters to send data at the same frequency at the same time, right? So by deploying base stations denser and denser, we are able to increase the frequency reuse higher and higher, right? So now we have achieved this frequency reuse 1 because different cells now will use the whole bandwidth everywhere, right? This is the standard deployment in LTE systems. So now the question is, moving forward, can we get higher frequency reuse? Obviously, that's needed, right? If we can do that, then we will greatly boost the network capacity a lot. So indeed, it is possible. And there will be many technologies. In the following, I will just introduce one. And indeed, what we believe would be the promising solution is device-to-device communications. So with device-to-device communications, these devices will be able to communicate with each other directly without the need of relaying traffic through the base station. And then, since the base station is still there, it will provide some basic assistance and also some controlling and monitoring of the communications between the D2D devices. And indeed, this has a great motivation to enable like proximity services, public safety, traffic offloading higher, and also try to achieve higher spectrum efficiency and energy efficiency. So indeed, it's a low-cost solution for reusing frequency in short-distance communications. And on the other hand, there's also a lot of challenges. Interference is always the most challenging thing. So for D2D communication, it's kind of a secondary medium access in multiple cell networks. Because when the devices are in the D2D mode, they can always choose to switch to the communication directly to the base station, right? So this direct communication between devices is something optional. You can choose to use it to improve your spectrum efficiency and energy efficiency. Or if you cannot do it, you can just fall back to the communication direct to the base station, right? So it's like a secondary medium access. It's optional. And then in this case, for this kind of hierarchical communication architecture, how should we design it, right? Indeed, for this new structure, there will be 2 levels of interference. And the one level of interference is the interference caused by the cellular networks. And for example, from the cellular UE towards other base stations, from cellular UEs towards the D2D links, right? For this part, I would say there's nothing that we need to do. For example, I mean, even there are interference from the cellular UEs towards D2D links, right? There's nothing we need to do because if the D2D links could not tolerate that interference from the cellular communications, you can switch to the cellular communications directly, right? So there's nothing we need to do here. On the other hand, there's also interference caused by the D2D networks. So for example, from the D2D links towards the base stations, from D2D links towards the other D2D links. So in this case, it's different. And indeed, we need to develop dedicated inter-cell interference coordination for D2D in this case. This is because for inter-cell interference, indeed, it affects the cell edge performance a lot. On the other hand, the D2D communications will happen a lot at cell edges because that's where communications in proximity will achieve the highest SNR. right? Because they are close to each other, so they will achieve high signal power. On the other hand, the interference is limited because they are far away from the base stations, right? So this is where the most problem will happen. And obviously, at the cell edges, there will be a lot of interference from other cells. So it is essential for us to consider this inter-cell interference coordination. And on the other hand, since we consider multiple cell joint design, it is essential for us to consider low complexity technologies. Because I mean, if you don't care about the complexity, it's always easy, right? It's always you can try to do the joint optimization across all cells, right? But the complexity is crazy. It will never go into practice, right? So the question is, how should we develop low complexity technologies to enable like efficient D2D communications to harvest the potential additional gain in frequency reuse? So this further illustrates these two levels of interference on cellular UEs and D2D UEs. So this, indeed, there will be some trade-off. If we want to achieve higher capacity, we can always use higher number of D2D links. But on the other hand, it will require more signaling overhead for the quality of service assurance. On the other hand, the technology needs to be scalable in the sense that since we consider multiple cells, there may be 10 cells, 50 cells you want to consider jointly, right? So your solution should not dependent on the cell size, right? Then it will be scalable. That's the idea. So the focus here would be to try to evaluate the scalability of D2C communication within cellular network. We consider the practical multi-cell scenario, and also we will consider the availability of CSI. So for example, we consider like there will be no CSI available to the D2D links. There will be some limited amount of CSIs, and there will be perfect CSIs, right? The question is, how should we do to deal with each scenario? So the design objective here is trying to maximize the frequency reuse. We want to see the potential of the frequency reuse here. So we want to maximize the number of D2D pairs that can communicate at the same time. Meanwhile, we want to assure the quality of service to both cellular UE and D2D links. So this is a simple math modeling. We have the quality of service constraint. The first, we have the SNR requirement for the cellular UEs, and we have the SNRs for the D2D links. Okay, both of these types of users should have their SNRs above their targets. Yes, like this gamma TH for this cellular UE, gamma TH for the D2D links. On the other hand, we need to keep something in mind. Whenever we introduce some D2D links in the cellular system, right, there will be some performance loss for the existing cellular users. It has to be there because if you don't tolerate any performance loss, you will not allow any additional D2D transmissions, right? Because D2D transmission then will always generate some interference. So the question is, how should we quantify that? Right. Then we introduce this so-called delta, this acceptable target CUE SNR loss. So for example, for the cellular users, right, their SNR target can be 15 dB, right? But on the other hand, in practice, their application may tolerate like 13 dB SNR. So in this case, it allows a 2 dB performance loss. And that's the amount of performance loss we can exploit to enable D2D communications. That's the idea here. All right. So we consider multiple cells. So this N is the number of cells. Okay, in each cell, there's this number of D2D links. Yeah. So here, this will be the design parameters. So if you look at the SNRs of the cellular user and D2D, there's this phi xk for D2D links. So this phi xk is either 0 or 1. So if it's 0, that means the D2D link is not enabled. If it's 1, that means it is using D2D communications. So it is basically this phi xk is like this mode selection indicator. Okay, and on the other hand, there's another design parameter which is the power used by the cellular user and D2D links. Right, here we focus on D2D links. So there are two sets of design parameters. One is this phi xk, another is pxk. So our focus is on the frequency reuse. So the frequency reuse in this case is defined as the sum of phi xk plus 1. Basically, this is the total number of simultaneous connections at the same time in the cell, right? And also this is the meaning of frequency reuse, right? It makes sense, right? Okay, good. So to maximize the network frequency reuse, the objective is equivalent to maximizing the sum of the frequency. Basically, we sum up the frequency reuse of all cells, and then we want to maximize. That's it, right? And the optimization parameters are the phi ij and the power. Okay. For this approach, one straightforward way is we can use exhaustive search to find the best power and mode selection for all the D2D links, right? So this is the optimal admission control. But in practice, this never happens because the complexity is just too high. So we are trying to simplify it and develop something simple. So we will try to use the approach based on statistical method. And here we are trying to estimate the interference based on the density of the D2D links in the network. Because the more D2D links you accept in the network, the more interference they will generate to the other D2D links and also to the existing cellular UEs, right? So we find this expected interference in a certain area, given the density of D2D links in that area. Because, I mean, for the density of D2D links, that's something very easy to obtain, right? The base station, they know how many D2D links are there in the network, right? So if we know the density, that's all that we need to know. And then we will be able to estimate the interference anywhere in the whole network. Okay, so this gives this idea. And then based on this, we are able to develop something very simple called distributed admission control. So with this distributed admission control, the D2D links will decide independently their active status and their transmission power. So we find two power bounds. One is called this lower bound to assure quality of service to each D2D link. And another is the lower upper bound to control the interference to cellular users. So the lower bound, this is the power you should allocate to meet your own quality of service requirement. So this is the lower bound for the D2D links. Okay. On the other hand, this upper bound is the power you should use, the maximum amount of power you should use, so that the interference generated to the cellular UEs from the D2D links is below the tolerance level. That's the idea here. Okay? So this can be calculated by each D2D link independently. That's the key here. And then after they obtain these two bounds, they know that, oh, this is the power I should use to meet my own quality of service requirement. On the other hand, I also know the amount of power I should use so that I won't affect the existing D2D, the existing cellular users too much, right? Then it's very simple. They will simply compare these two bounds, and if the lower bound is smaller than the upper bound, then know, oh, it's safe for me to transmit. I can communicate in the D2D mode. That's the idea. And on the other hand, if we want to maximize the frequency reuse, that's also another key. The transmit power should always be selected as the lowest possible. That is the lower bound. Because when you are minimizing your transmit power, you will allow more other D2D links to transmit at the same time, right? That's quite straightforward as well. So indeed, this approach is compatible to the LTEA standard. So in LTEA standard, they have already had some kind of transmission power configuration for transmission for D2D links, right? And then all they need to do is just applying this minimum power requirement, choose the minimum possible, and then you can use it. And then you will be able to maximize your frequency reuse. So now let's take a look at some more from the signaling perspective. In order to implement it, this base station can simply get the active status of D2D links and then calculate the number of active D2D links. Okay? And then they can simply exchange the number of D2D links in the cells. So this is also kind of like exchanging the frequency reuse number in different cells. Because it's the same, right? If you know the frequency use, you know the number of D2D links in the cell, right? So these are equivalent to each other. After you exchange it, then you broadcast these parameters. Then the D2D pairs, they will be able to calculate by themselves and then know if they should transmit in D2D mode and what power they should use based on the lower bound and upper bound. So it is very simple. It's just a couple of equations, 3, 4 equations. Of course, there are tons of equations when we derive this thing, but this is the result. It's extremely simple. So now let's see what we can achieve. Indeed, based on our result, the frequency reuse above 10 is absolutely achievable using this simple D2D technology. So on the left side, it shows the CDF of the number of D2D links. Okay, so this one is the one based on exhaustive search. Basically, this is the optimal approach. And then with this simple distributed admission control, this can achieve this. So you can see it can achieve easily 10 simultaneous D2D transmissions, communications in a real multi-cell network. And these are the other approaches based on single cell designs. And on the other hand, this one shows the improvement of spectral efficiency. So you can see by using D2D and also this multi-cell design, the spectral efficiency is dramatically increased from this maybe 5 bits per second per hertz to 50 bits per second per hertz. So it's 10 times increase. That's a lot, huge. And this shows the spectral efficiency. And here the x and y axis are the 95 percentile cellular UE SNR losses, and this is 5 percentile SNR of active D2D links. So basically, these are performance requirement of the cellular users, and then this is the performance requirement of the D2D links. Okay, this red surface is using the distributed design across different cells. So basically, it's like IC for D2D. Right? You can see the performance is much higher than the other approaches. The one at the bottom, at the bottom here, is the one that considers only single cell design. It also enables D2D, but it only considers this single cell design. There's a great limitation, but by considering multiple cell jointly, we can see the performance boost is amazingly high. On the other hand, the D2D is effective in increasing both spectrum efficiency and energy efficiency, indeed. And here you can see this is the x-axis is the average spectrum efficiency, and the y-axis is the average energy efficiency. So basically, this is showing the spectrum efficiency and energy efficiency region of different approaches. So this, in this corner, is the case when we don't use any D2D. So you can see this is the achievable spectrum efficiency and energy efficiency region. It's within this small corner. But on the other hand, if we are using D2D, this region is greatly extended. It's like, I would say, how many times? It's 6. It's like 36 times improvement in the area, the coverage. So you can see these users, they can achieve this spectral efficiency and energy efficiency region at these dots. And of course, you can further, here this is based on simulations. You can do some further theoretical analysis to show what's going to be the bound of the spectral efficiency and energy efficiency region without D2D and with D2D. And you will see indeed there's great potential there. Right. So to harvest this 10 times frequency reuse, and first we can see that D2D is quite potential. It's a very promising solution, right? It can achieve more than 1,000% increase or 10 times increase of spectrum efficiency and energy efficiency. On the other hand, it only requires negligible performance loss for the existing cellular UEs. So on the other hand, to maximize the frequency reuse, it's essential for us to use the lowest possible transmit power. And also, this multi-cell joint design is essential here. Because you can see, if you use only single cell technology, their performance is very low compared to this joint cell, like that considers IC, right? It's a dramatic improvement. So new IC needs to be developed to handle this D2D interference. And it's 10 times free capacity boost. You don't need to install anything else. No more antennas, no additional spectrum, right? So only software update or whatever. So it's free. Game.